Hello friends, welcome to YouTube channel Electronics for You. Friends, in this video I will explain transient response specification for a second order system. Note here that it is just a transient response specification, but generally we consider it for the second order system because in our previous video where I have explained the first order system in details, and after that I have taken some examples of the first order system. In the first order system, we generally calculate T and K, that is desiccant and time constant. So here in case of a second order system, generally there are many parameters which is to be considered, and basically these parameters, note here that second order systems parameters are depending on the form of a response. Generally we are having two forms of response. One is oscillatory and another one is exponential. In this case we will consider the oscillatory system, and here it is a second order system. The transfer function for the second order system is given by this equation, that is omega n square divided by s square plus 2 zeta omega n s plus omega n square, where omega n is our undamped natural frequency. Mostly it is called as natural frequency, which is the maximum frequency of the oscillation for the second order system. And here zeta is basically a damping ratio which will resist our response, and therefore further our response will be stable. Okay, on the basis of that, generally depending on the damping ratio, it may have the value from 0 to 1. Maybe it is having 0 value or 1 also, but if it is having range within 0 to 1, it is called as underdamped system. And for underdamped system we are explaining the following parameters, which are nothing but delay time, rise time, peak time, maximum overshoot and settling time. So these are the parameters which will be explained in this video. Note that omega n is always greater than 0 because it's the frequency and it will have some natural values. So this is the characteristics of a second order system. And note here that the response is oscillatory in nature. You can see here that the response is oscillating between our reference signal and its tolerable limits. So it's the underdamped system where the parameters are delay time, rise time, peak time, maximum overshoot and settling times, which can be indicated here. So on the basis of this diagram also you can define these parameters, but also you have to remember the formulas related with it. So the first parameter is delay time, and note here that delay time is this one. It is starting from this point, means it is time axis, x-axis is our time axis, and it is starting from this point to this. So delay time is, you can see here that the response is reaching to 50%, or we can say that it is reaching to the half of the reference input, or we can say that the half of the unity. Okay, so delay time can be defined as, it is the time required by the response, to reach half of the final value for a very first time. Okay, so this is delay time. Its formula is 1 plus 0.7 zeta divided by omega n, and it is indicated by TD. Its unit will be definitely seconds because it is a time. Now after delay time, the next specification is rise time. Now again you can look here from the diagram, the output is varying from 0 to 100% in this case because it is an underdamped system. So rise time can be defined as the time required for the response to rise from 0 to 100% of its final value. Basically for underdamped system it is 0 to 100%, and for overdamped system it is 10 to 90%. Okay, so this point is to be remembered again. The formula for the rise time is given by TR equals to pi minus theta divided by omega d, where this theta equals to tan inverse under root 1 minus zeta square divided by zeta. So this is the formula for tan inverse. Just put the values and calculate. You will get TR, that is rise time. Again, it is expressed in seconds. The next is peak time. As you can see, this peak time can be measured up to this point. Now this to this point, and note here that it is our maximum output. It is maximum output in the first attempt, that is percent MP, sorry, that is MP, that is peak overshoot. So our peak time will be measured from starting to up to this point. Peak time is the time required for the response to reach the first peak. Note here that it is the first peak, to reach the first peak of the overshoot. Okay, so this is peak time, and the formula is pi divided by omega d. Now next is definitely this maximum overshoot, or we can say that it is peak overshoot, which is indicated by MP. And note that it is starting from this point to maximum point. So it can be defined as, the maximum overshoot can be defined as the maximum peak value of the response curve measured from the input signal value. Also note that it is measured from the input signal value, which is nothing but the unity. Now this maximum overshoot is the maximum error between input and output, because at this point our response is reaching to the maximum value, and therefore it is the maximum error between input and output. And generally this maximum overshoot is expressed in percentage. So we can write the formula for this as percent MP equals to e raised to power minus zeta pi divided by under root 1 minus zeta square into 100, because we are expressing it in the percentage. And generally this maximum overshoot will directly indicate the relative stability of the system. Means maximum overshoot percent MP, we can say that it will always indicate the relative stability of the system. The next parameter is settling time, and you can see here from the graph, this is settling time TS. It is up to this point. So this is the response which is going into the saturation here, going into the stability here. So it is our, this dotted line is indicating our allowable tolerance limit. Generally it is considered as 2% or 5%, and if we do so, then settling time is defined as the time required for the response curve to reach and stay within. Note here that we have to reach up to this point, also we have to stay within this tolerable limit, because this response is in the means it is at the final value near this point also, but after that it is breaking this barrier of tolerance limit, and therefore it must be within, stay within the tolerance limit, and therefore settling time is measured up to this point. Okay, and here again usually this limit is 2 or 5%. The formula for the settling time is given by Ts equals to 4 divided by zeta omega, 4 divided by zeta into omega n. So in this way, these are the different time specification, and further we will see some numericals based on this. Thank you. And friends, if you like this video, please subscribe our channel and press the bell icon for notification, and like, comment and share. Thank you.